I'd like to welcome you to Graphs in Criminal Intelligence webinar. It is a webinar run by us, GraphAware, Mission Critical Graph Analytics. We're glad to see so many of you joining today. My name is Ondřej Peterka. I'm the Marketing Director at GraphAware. And today it's my utmost pleasure to introduce you to Dan Newland, our General Manager of Australia and New Zealand. Dan has incredibly extensive experience with implementation of graph technology in federal government agencies. So today he will be sharing his knowledge with us and also with you. Before we get started, a few house rules. First of all, feel free to ask any questions. You can use the Q&A button down as a Zoom function. These questions will be just seen by us, by Dan and me. So we will then take them and answer them by the end of the session. If we do not get to all the questions, we will just send back answers one by one. The other point is the webinar gets recorded. So in case you miss anything, you can always get back to what you missed, and we will be sending you the recording shortly after the webinar. So without a further ado, I will hand it over to Dan, who will walk you to the webinar. So thank you again for joining and enjoy.
Excellent. Thank you, Ondřej, and hello, good morning or good evening, everyone who's on the line. We've got a lot of people from across the world here today, so really great to see such a large audience here for this presentation. Now, Ondřej gave me a little bit of an introduction, but for a bit more background, I've been working with graphs for just over 4 years now. I was first introduced to them when I worked as a team leader of data science at the Australian Federal Police here in Australia. Then moved into a role of director at the Australian Tax Office, again working on graph database implementations, and now working at GraphAware as the general manager for Australia, New Zealand. So I've kind of been riding that graph wave, that hype cycle wave for the last 4 years now, and really pleased to be here in this role today with GraphAware. We've got a lot to cover today, so I'm going to get straight into it. We're going to start with a very, very brief elevator pitch for what Neo4j is. We're going to talk about what is Hume as well. And then we're going to really spend most of our time here today talking about how graphs solve the challenges of modern intelligence analysis and practical implementation tips and tricks for law enforcement and intelligence agencies that are trying to implement graph. We're then going to do a live demo of Hume walking through an intelligence case and show some of the features and functionality that we have available in the Hume platform. So really quickly, we're going to start with what is Neo4j. When we think about databases, generally we think about relational databases, columns and tables, whether it be Postgres or something like Excel. We think about data being arranged in this particular format where our entities are stored in columns and each different row is a different instance of those specific entities. Graph kind of flips that on its head. It takes the entities out of that store and then extracts the relationships from that store and represents them as nodes and relationships interconnected in a database in a graph native store. So really there's 3 data formats or 3 ways data is stored in a graph database. We have our nodes, we have our relationships, and we have our properties. So in this particular example, we have a person, event, and a location node. So rather than storing that as columns and rows in a relational table, we store it as entities and connected relationships. So in this particular example, we see Amy Peters is involved in a homicide case event, which is located at a particular location of interest. So we have nodes, relationships, and then properties on each of the nodes and relationships. So just a really quick elevator pitch. I know most of the people in this audience are probably quite familiar with Neo4j and Graph, but just the elevator pitch for what that data store looks like. What is Hume? Well, when you have a Neo4j instance, you need a way for intelligence analysts to be able to quickly and easily interact with that Neo4j instance. And so Hume is the mission critical graph analytics solution that sits on top of a Neo4j database and makes all of the powerful network and graph analysis available to intelligence analysts with the click of a button. So intelligence analysts don't have to learn Cypher, they don't have to learn graph theory, they don't have to learn graph data science. All of that becomes available to them in a really simple and easy to use interface, which allows them to search, visualize, and analyze intelligence graphs. So a little bit of history. Intelligence or link analysis is not something that's new to intelligence analysis. The earliest Now, a recorded thing that I could find on the internet was from 1975, a paper published in 1975 that said link analysis procedures were used by officers and the results confirm the utility and potential value of these procedures. But in truth, link analysis has been conducted in intelligence and law enforcement for decades. We've come from the corkboard, like we can see in the image there, with the string and the pins attached to images and to notes, to the canvas. So relational tools like I2 Analyst Workbench and other visualization tools that sit on top of relational stores. That was kind of the second generation of link analysis. And now we've come to the third age, or the third generation of link analysis, which is a graph native store to do link analysis. And there's a lot of reasons why that is a powerful thing to combine. When you think about the most common intelligence use cases and the most common intelligence questions, most of them are graph-based questions. So show me how person X and show me how person Y are interconnected. It's a graph-based traversal that we can do along the relationships and intermediary entities between two persons of interest. Show me how a gang is sourcing funds is something that we can do flow of funds analysis for, which is a perfect graph use case to observe how money is flowing in and out of a particular network or group of individuals. Show me communication events between two individuals. Again, we can easily traverse phone calls between multiple entities and see how communication networks are behaving between entities of interest. And finally, who are the most influential parties within a criminal organization can be easily solved using graph data science to detect, who's the most important person in a particular network, who's the most connected person in a particular network. So these most common intelligence analyses questions are actually graph-based questions that can be gain a lot of benefit from having a graph-based store. Now, some of you are probably thinking, well, if we've got 3 generations of relational tools here and 3 generations of link analysis, why can't this be done with the existing tools? Why can't all those questions that we just talked about be done with existing tools? And the answer is they can be done with existing tools if you're willing to accept some pretty significant limitations. The first limitation is that tabular tools will never be as efficient as Neo4j graph databases to return complex network traversals. They're never going to be able to do that traversal logic and as efficiently as a graph store is. They're also not going to be able to solve complex pathfinding and graph algorithms easily. It's going to be difficult to implement that, whereas it's seamless to implement that with a Neo4j store. And they're going to be slow and provide a poor user experience. The final point is a really important one, is that they don't enable visual graph exploration. So in intelligence analysis, a lot of the time you don't know exactly what you're looking for, and you want to ask the data, show me the answer to this particular question that I'm interested in. A graph is really good for this. We don't have to define how two entities are connected and how two entities, how that traversal logic should appear. We can just simply ask the data, do that traversal for us and show me how these two entities are connected. And one of the organizations I used to work at is a great example of a relational system being replaced or enhanced by a graph system. When I was working for a financial agency, we had a relational system there that was built in the early 2000s that was able to traverse networks of individuals to calculate suspicious transactions and suspicious sources of wealth. That relational system developed in the early 2000s was really sophisticated for its time, but it was only able to get to a depth of 5. It was only able to traverse that relational database to a depth of 5, which meant that the results and the final outcome of this algorithm was significantly hampered. When we started to implement a graph-based solution, we were able to see depths of 45, so transaction depths of 45 between particular entities of interest, and return that result much quicker and get a much faster response out of that result. So just one example of how graph systems can replace and enhance some existing relational solutions. So the challenges of intelligence analysis, or the challenges that intelligence analyses teams face. The first is siloed data sources. The second is siloed analytical tooling, relational stores for network analysis, ad hoc data collection, manual analysis, and enormous data volumes and data variety. We're now going to walk through each of these 6 and explain how a combination of Neo4j and Hume can help to solve some of these some of these particular challenges. The first is siloed data sets and siloed data. I'll use an example of an organization that I spoke to some intelligence analysts at, and I asked them when we were in the project development phases, I asked them how many data sets and how many systems do you have to interact with on a day-to-day basis to conduct your work. And this intelligence analyst said, I interact daily with about 22 individual systems, and those individual systems are completely disconnected from one another. And so if I want to do analysis, I have to kind of handpick information from all 22 of these, bring them into some unification tool, something like I2 Analyst Workbench or something like Hume. I have to pick all those things out, and I have to try and analyze them in a kind of common canvas. But those 22 data sets are completely disconnected from one another, meaning that we have to search through dozens of data sources to find the information that we're looking for to do a particular search. And again, this comes back to that point that I made earlier, is that if an intelligence analyst is doing this, to some degree, they can only search and find what they're particularly looking for, right? Whereas if we connect that data set natively, we don't have to predefine traversal logic or data that's needed to do that traversal logic. So the solution to this using Neo4j and Hume is to create a single view of intelligence. So we ingest the entities and relationships of interest from those source systems, we make them searchable, and we make them connected. And that single view of intelligence means that an intelligence analyst doesn't have to go to those 22 or however many systems of interest it is to do a search and to find how entities are connected. They have a single view of intelligence so they can go into, they can search for an entity that they're looking for. They can see the representation of that entity from the multiple systems that have been ingested, and they can see how that information is all connected both within those systems and between those systems. So that single view of intelligence really breaks down that data silo and makes it easier for intelligence analysts to do their searches and to do their work. The next is siloed data capabilities. Now, it's a little bit hard to see in this photo, but I often think that the reason that when we see intelligence analysts on TV shows and on movies kind of covered in screens that all have rolling Linux code running on them is because that they have so many analytical tools at their disposal. They might have five individual analysis tools, one for geospatial, one for financial records, one for call charge records. The list goes on. They have many different disconnected systems that try to give them some capability that can't be achieved outside that system. So really disconnected data and disconnected capabilities to analyze that data. So many distinct platforms leading to fragmented analysis findings. So those systems might be really good at analyzing a particular domain or a particular data set in isolation. But when it comes to connecting that data between the different capabilities and between the different domains is where this starts to become a significant issue. With Neo4j and with Hume, we create one canvas with many analysis capabilities. So on the same screen, you have access to all of the data like we talked about previously, all of the siloed information presented in one screen. But we also allow for geospatial, temporal, and advanced graph data science to be run on a single screen, which means that you have a single canvas to understand the where and the when of crime, detect emerging crimes and trends within criminal networks of interest. You don't have to export something from Hume and analyze it in a geospatial tool, or export something from Hume and analyze it into a temporal tool. All of that capability is presented to you and available in a single canvas, which means that you can analyze your networks of interest from the many data sets that we've ingested, and you can also analyze them over time and over space in geospatial. The third one is using tables to analyze criminal networks. So we're used to, as I mentioned at the start, link analysis has been using relational systems for decades now. I2 Analyst Workbench is a great example. Yeah, it has a relational backend store with a graph visualization tool over the top of it. So we're using columns and rows and columns to analyze networks and graphs, which becomes a real challenge for a number of reasons. One is that it's a slow and unresponsive, or often a slow and unresponsive user experience. The second is that we can't ask those really complex questions efficiently and effectively if we have a relational store as opposed to a graph-based store. So not until we get to a graph-based store are we able to run complex analysis efficiently and effectively. Now, obviously, Hume's solution to this is to have a Neo4j graph database backend, which again makes all that information searchable and connected in that graph store. So it's a graph-based analysis and visualization tool with a graph-based native store, which means that we can quickly and effectively, answer those complex questions in a graph. The next example is ad hoc data collection. And the example I use here is a story from a law enforcement agency that I was speaking with recently. They were working on a particular homicide case of interest, and they found a shoe print at a crime scene. And they gave that to their forensics team, and the forensics team were able to isolate it to a particular brand of shoe, which was then found to only be sold at a particular store in a particular location. So all of a sudden, intelligence analysts and investigators were trawling through the customer receipt records for a particular store selling a particular shoe. You're never going to have a database or a data connection set up to analyze that data automatically. You're not going to have a shoe record database set up in an organization. And this is something that's relatively unique to law enforcement, is that there's always going to be ad hoc data collection that occurs in investigations and task forces and in intelligence analyses. And so analysts need a way to be able to take that raw piece of information, analyze it in some kind of sandpit or sandbed area, either throw it away or discard it if it's not useful, store it locally if they need to store it locally, or add it to a corporate or shared information store if there is something significant there. The way that Hume solves this is to have a product called Hume Orchestra, which streamlines ad hoc data ingestion. It creates a drag and drop, or provides a drag and drop interface so that analysts can quickly and easily upload and map data sets to a particular schema of interest, which means that analysts can take that random piece of data that they've just received and they can quickly upload it to a graph and do their analyses, adding that information to that single view of intelligence if they want to. But more often than not, these data files are discarded, if nothing significant is found. But Hume Orchestra provides that tool to quickly and easily upload and analyze, and allow analysts to analyze ad hoc pieces of data. The next one is volume and variety, and particularly in the digital forensic space, where officers and agencies are seizing mobile phones, they're seizing computers, laptops, servers, email dumps. There's a huge volume and variety of data that law enforcement agencies and intelligence agencies are coming into contact with. And it can be incredibly complex for intelligence analysts to be able to sift through all of that information and find the key pieces of information that are relevant for them on a particular investigation or a particular operation. It's a significant challenge to extract the right amount of information from these sources. We get terabytes and terabytes of data in a particular server dump. What's the information within that server dump that's actually meaningful for either the operation that we're working on or for an intelligence store across the organization? So what Hume does to solve this issue is allow us to extract insight from complex data types. So in the right-hand example there, we can see a screenshot of a photo processing use case that we've worked on previously, where faces were given a digital fingerprint across multiple different photos. Those digital fingerprints were then loaded into a graph, and when co-occurrence in photos occurred, we created a relationship between two digital fingerprints. We then tied those digital fingerprints to identity stores or identities that were identified somewhere else in the data set. So we reduced that information down from all of these photo dumps down into a single relationship that occurred between two entities of interest that said person A appeared in a picture with person B. And for intelligence purposes, that is the key piece of intelligence that needs to be extracted for them to do their analysis. And Hume provides a way to extract that, provides a way to a destination for that information to be stored in a graph database and presented to intelligence analysis. So that example is a photo. We can also do it with the destination for video algorithms or the outputs of video algorithms, as well as documents and natural language processing as well. And the key thing to remember here for intelligence use cases is that we're trying to extract the key pieces of information, the key linkages and the key entities that are relevant and useful for intelligence analysis. So it's not about dumping everything into the graph. It's about extracting what's actually meaningful and useful for intelligence analysis. The final one is really a conclusion of all of these different steps, is that manual analysis. Intelligence in the modern era, unfortunately, is plagued by manual analysis. Intel analysts are constantly manually collecting data, manually organizing data, manually loading it into whatever tool they're using, whether it be I2 Analyst Workbench, Excel, or something else. They're constantly plagued by manual steps in this process. They're often responsible themselves independently to source, clean, extract, load, and do the entire life cycle of data analysis, which means that they're plagued by these manual steps. There's a number of features in Hume that help with this, but one of the biggest ones for analysis is a concept in Hume that we call actions. And we're going to see actions when I jump into a demo shortly, but actions allow you to automate intelligence analysis. And I'll explain them a little bit further when we get to them in the demo, but essentially what it allows you to do is your data science, data analysis, data engineering team are able to write Cypher code snippets that are parameterized for what's on your canvas. An intelligence analyst with a click of a button can run that code to do that particular analysis. So it helps to streamline and automate some of that analysis step in the process. And we'll see some really good examples of that when we get to the Hume demo shortly. Okay, the next thing we're going to talk about is some practical implementation steps for intelligence graphs. We're going to talk about some of the different types of graphs that we see in the intelligence domain and how Neo4j and Hume can support the development of graphs in this particular way. So we talked before about the different elements of a graph database, so the entities, the relationships, and the properties that can be loaded or can be defined in a schema. One of the questions that we get at GraphAware being a Neo4j consultancy is, what is the optimal schema for us to use? And the answer is, unfortunately, it depends. It depends largely on the use case and the users that you're dealing with and interacting with. On one extreme, you can take your 22 source systems and you can load them into an extreme schema that is just a single entity object with a single relationship. So things, you just summarize everything to be things that are related to things. In a schema view, you end up with the left-hand side, which is a single node and there's a single relationship tied to it. Now, this is obviously flawed. This is an extreme example, but it's just to illustrate that schema creation happens on this spectrum. And this is the far end of the one side of the spectrum where you summarize all that information into a single entity and into a single relationship. And when that scheme is instantiated, you end up with the right-hand side. So things being connected to other things. You know, they might be persons, they might be phones, they might be vehicles, whatever it is, but they're things that are connected to things. We don't have any definition of what those things are in a schema view. And all of that information then gets dumped onto the properties of those things. Now, I said I'm not recommending this as an approach. I'm just illustrating that it's one end of the spectrum in schema creation. The other end of the spectrum is to go absolutely crazy. And every possible entity that you can represent that entity, and every possible relationship connecting those entities, represent those relationships. In the first example, it's going to be very difficult for us to write Cypher code to be able to do traversals because we're going to have to constantly be referencing properties on the nodes, which is going to be inefficient query. We end up with a similar sort of scenario here where it's going to be very difficult to write Cypher queries for this graph because we're going to have to reference every specific element that we want to reference at every specific step of a traversal. So the perfect schema exists somewhere between these two extremes where we summarize everything down to one node and one relationship and we create everything possible. Really, when you're doing schema design, you have to consider your use case and you have to consider your users. So it has to be use case driven. So ask yourself, who are the users of this graph? Who's going to be consuming it? What type of analysis do they want to conduct? What type of data do they need to meet their requirements? How many of those source systems are we talking about do they need to be able to meet their use case? And probably from a technical perspective, what's important to consider is what queries are going to be written to meet that use case. There are some simple rules that you can apply where if you're referencing something if you're constantly referencing something that's a property, then maybe it should be considered a relationship or a node type, a first class node type. But you really need to ask from a technical perspective, what are the queries that are going to be written and how can we efficiently create a schema that's going to serve those queries. Remember, with Hume and Neo4j, the schema is flexible and can be iterated. So you can start with something simple, and then if you find that your queries aren't running efficiently and effectively, you can make tweaks to that schema very, very easily. There's a lot of flexibility available in both Neo and Hume to do that. In the intelligence domain, we really see 4 types of schemas or 4 types of graphs that get created. The exploratory graph, the domain-specific graph, the tactical graph, and the sandpit graph. I'm going to go through each of these 4 and talk about what they look like in the intelligence space. The first is exploratory. Pole is a great example of an exploratory graph, which is person, object, location, and event. It's a very famous schema design and basically summarizes information from a number of different source systems into a really simple and easy to understand schema. They're simplified, these exploratory graphs are simplified representations of many sources of information, and that it makes intelligence findings easily accessible. It's very easy to see how entities are connected in this particular model. It's useful for when analysts don't know what they're looking for. They just want to understand how two, let's say, persons of interest are connected, and that summarized traversal between the two of them makes it easier for them to see that. So you can ask questions like how a person X and how a person Y connected to one another, and we can actually traverse through multiple sources of information to get that answer. So here's an example of that. We have 3 entities, and these entities are uniquely created across source systems using entity resolution and entity disambiguation. There's a lot of theory that goes behind here, but for this presentation, let's just assume that those entities are uniquely created. There's a lot of different ways to manage that and to track that lineage and that connection. But for this use case, let's just say that they're uniquely created across systems. Relationships are then summarized and attached to the entities that they're created. So what I want to draw attention to in particular is that called relationship between Ben Smith and Steve Jones. That's a summarized representation of a phone call. The phone that's used, the time that phone call happened, maybe the cell tower, the location of that call is all stored as properties on that relationship. It's not stored as nodes or as relationships. It's stored as properties on that relationship. So it's a summarized view of that call to say that Ben Smith called Steve Jones. The same thing with the pictured with relationship. We talked about some use cases where we can analyze facial recognition fingerprints and create those simplified relationships. Well, here's a great example of that, where we have a pictured with relationship between Steve Jones and Jane Doe. So we've got advanced relationship extraction from pictures and text being summarized down into a really simple and easy to analyze form. The point that I'm trying to make here is that we don't have the full context for all of these domains present in this exploratory graph. We have a simplified, summarized view of the information that makes it very easy for analysts to go in and see how these 3 entities are connected to one another. We can imagine, and we're going to get to domain-specific graphs next, but we can imagine if we had a more complex schema here where we had mobile phones and we had pictures and things, intermediary nodes between each of these entities, it would be a much more complex picture that would be presented on our screen. And it would be a much more complex analysis required to be able to get to this outcome that Ben Smith called Steve Jones and Steve Jones was pictured with Jane Doe. So the exploratory graphs are designed to summarize that information and make it accessible for intelligence analysts in an easy to consume way. The next is domain specific, and domain specific really presents information in its full context for the particular domain. So we can see in this example, we've got a telecommunications domain graph. We have cell towers, phone calls, phones, IMEIs, IMSIs. All of the rich context of telecommunications is presented in the domain specific graph. So where in that previous example, we just represented a call as a relationship between two entities or two persons, here we would have the full context of that call. We would have the phone numbers that we use, the cell towers that we use, the locations of those cell towers, the IMEIs and IMSIs used on either of those phone calls. But if we tried to present this to Intel analysts in that first example where we're just trying to see how two entities are connected, we might be able to get away with it if we had one domain or two domains. When you get to 4, 5, or 6 domains, your scheme is going to get clustered and cluttered quite quickly. So it's very difficult for analysts to actually get to that outcome that we found in the previous example if we clutter the schema and clutter the visualization with too much information. So domain-specific graphs are designed to separate us away into our domain, and that there's a connection between that first exploratory graph and this domain-specific graph as well. So as I said, domain-specific graphs provide the detailed representation of a particular context. They show the full context that is relevant to that domain. It allows you to drill into the details of the data. So let's imagine that we're intelligence analysts and we're working on that exploratory graph example where person A called person B. I can select that call and I can go to my domain graph and I can see the full context of that call without cluttering up my visualizations or cluttering up my analysis canvas. You can have multiple sources of data within the same domain. So let's say there's 3 or 4 sources of telecommunications information. There's no reason that we can't represent those multiple sources of information within the same domain in the same graph. But it is important not to mix domains, or at least not to mix domains too much, because what we're trying to achieve with these domain-specific graphs is to have the full context of that domain without cluttering the canvas. So we want to try and keep it to one specific domain. And the use case for doing that exploration between domains is what the exploratory graph serves in its summary. So we're going to our exploratory graph, we're finding the key linkages, and then we're hopping into our specific domain graphs to get the drill down context of those particular relationships between the entities. And again, if you do start to mix domains quickly, your visualizations and your queries are going to be cluttered and unoptimized. So important not to mix those domains. So in the previous example for exploratory graphs where we represented a phone call just as a single relationship, here we have the full context. So we have a number on the left-hand side having a phone call event with a number on the right-hand side. And we have the full context of the cell phone tower that was used for the call, the IMEI on either side, the IMSI on either side, a transcript of that call if that's available as well. So we have the full context of that piece of information without cluttering our canvas with multiple domains and making it difficult for intelligence analysts to find the key linkages that they're looking for. The next is tactical, and tactical graphs are really designed to be a blend of domains for a specific operation or for a specific investigation. They're created to serve a specific operational use case. So, perhaps there's a long-running investigation going on for a particular outlaw motorcycle gang or particular entity of interest. Tactical graphs are created to blend those domains for one specific use case or one specific investigation. They blend in the corporate data sets, so those 22 sources that we keep talking about, they blend together those corporate data sets, and they also bring in their own specific files that are specific for that operation and only really relevant for the context of that operation or the context of that investigation. They're not something that we want to share with the wider organization, possibly because it's sensitive, but also possibly because it's not useful outside of the context of this particular investigation. Access to tactical graphs is often limited to a small number of users, so the people who are working on this particular investigation or or task force. And as I said, some data is only relevant or usable within a specific context. So maybe there's a piece of information that we obtain that can only be used for this specific context, and it can't be used outside of that context. That's where a tactical graph comes in. These graphs are generally collaboratively built and populated by intelligence teams. So essentially what you're doing here is you're taking information from your domain-specific graphs, that's the corporate data sets that we're talking about, and you're merging that together with information that can only be viewed or analyzed by a specific smaller audience. And what that allows you to do then is see the connections between what we know as an organization and what we know as a task force and as an operation, and provides that blended canvas to analyze the linkages between those two things. And finally, sandpit graphs. As the name might suggest, sandpit graphs are about analyzing those ad hoc data sets that we come into contact with in law enforcement and intelligence. So maybe it's a receipt log from a shoe manufacturer or a shoe store that just wants to be analyzed in a one-off fashion, and then we either discard it or we store it or pass it on to other corporate data sets. Sandpit graphs allow analysts to upload their data file using Hume Orchestra and analyze it in a graph. So a graph is a really powerful tool for analyzing these particular files. And these data sets can be merged into the tactical or domain graphs if required. So if you find something significant, we can merge it into a tactical or a domain graph if and when required. But more often than not, just given the large volumes of these ad hoc data sets, these files are often analyzed, conclusions are drawn, and then discarded if it's not of use. The important point here is that sandpit graphs give all of the benefits of having a local instance of Hume with all of the benefits of having a server-based application. So you have the grunt of the server, the processing power of the server, but it feels like a local graph or a local instance of Hume. So to summarize those key points, important considerations for intelligence graphs: really consider your graph schema. Think about which of those 4 types of graphs you're trying to create for your particular use case. You always have to keep your users in the front of mind, particularly in the graph schema creation phase. And a graph that is developed for all use cases really is optimized for none. It's not optimized in a visualization tool for analysts. It's not optimized in a technical sense for queries. If you're trying to develop a single graph to serve all use cases, you're not going to create an optimized experience for either the analysts or the developers on the platform. And that's where you need to keep in mind those exploratory graphs and those domain graphs underneath them as well. Alrighty, we've raced through the slides, which is good. We're going to move into a Hume demo now, and I'm going to do some intelligence analysis using Hume. So just bear with me while I swap screens here. And I'm just going to pop over into my Hume instance that I've logged into. Now we can consider this a tactical graph. We've got elements of our domain-specific graphs loaded in here, and we've got some ad hoc files or ad hoc relationships that have been created for this particular case. Now for this particular instance, what we're looking at is a car theft between 2 entities of interest. One of the entities we know has some connections to organized crime, but we have a suspicion, our investigators working on this case have a suspicion that maybe the victim here isn't necessarily completely innocent either, and they've asked us as intelligence analysts to jump in, have a look at the data that's available, and help them to make some inferences about the victim's actual victimhood in this particular case. So what I'm going to do now in the first case is search for Billy Moore, and Billy Moore is our alleged perpetrator. In this example, and in the Hume search bar at the top, I'm just going to do a full text search on the underlying Neo4j database. And I can see here when I search for Billy Moore, I get my search results coming back, just a single search result in this demo environment. But I'm going to add Billy Moore to the canvas. Just going to swap my style off here. We'll talk about styles in a little bit. But we can see here, I get Billy added to my canvas. If I click on Billy, on the right-hand pane, I can see the properties pane, and I can see all of the attributes that are tied to that particular node. In this case, we've just got NHS numbers, some name details, and some criminal and risk score attributes that are created there as well. We'll talk about those in a little bit. If I right click on Billy and I go to the expand window, I can see all of the relationships that are tied to that particular entity. Now I can do some manual analysis here. I can click on specific relationships, and I can do some manual exploration of the graph, just traversing through. If I double click, it's going to expand everything, and I can continue going through like this. But when we've been asked a specific question or asked to analyze a specific thing, analyzing or exploring the graph in this way is going to quickly get out of hand. Already we've got 30 entities on the screen. With a couple more double clicks, that'll easily be 100, and then we'll be into the several hundred if we just do this manual exploration of the graph. So what we want to do is something that's a little bit more tailored. So we know in this particular example, Billy was involved in a crime, was party to a crime that involved another party called Lewis Hughes. So I'm going to search for Lewis Hughes. I'm going to add him to my canvas when that result comes back. You can see there's Lewis there. And we'll just get on the screen the representation of this particular crime. We know that Lewis owns a car. That car was involved in a crime, and Billy was the perpetrator of that crime. So we see there we have the graph representation of the case that we're talking about. This is where, as I said before, we introduce the concept of actions. If I go into the right-hand pane here, we can see we've got a few actions available. Actions are essentially pre-compiled code snippets that developers have put together for us as analysts to be able to quickly and easily analyze the graph in an automated way. So we can see here we have lots of different types of actions, global actions that run on the whole graph, local actions that run on a single entity, multi-selection actions that run with two parameterized entities or multiple parameterized entities, and many, many more action types. The return types as well, we can have graph-based returns, we can have chart-based returns or table returns. Lots of flexibility here in how the results are presented to the analysts. And finally, down here, we have the cipher code that is used to generate a particular or used in a particular action. So actions allow us to automate and streamline that analysis process for analysts. Now, the one I'm going to run first, or the one that's interesting for us in this case, is what we call proximity to organized crime. And essentially what this action is going to do is going to start at Billy Moore, and it's going to try and do a traversal to a organization that's been deemed organized crime or been classified as an organized crime organization. So I'm going to click on this, and we're going to see a very obvious connection between Billy Moore and the Hells Bells outlaw motorcycle gang. So maybe not all that interesting. We probably could have found that one ourselves if we were just right-clicking and exploring. But in this particular case, our investigators have said that they have suspicion that Lewis Hughes might be involved in organized crime as well, and maybe that this isn't he's not a completely innocent party in this example. So this might be interesting for us to right-click on Lewis and run that same action, proximity to organized crime. And we do get an interesting result coming back for this particular example. We have Ernest Thompson, who has a family relationship. It's Lewis Hughes' son, has a connection to the Hells Bells outlaw motorcycle gang. So first clue here that maybe something's not quite as it seems, or isn't quite as it's being, the truth isn't quite being told in this particular example, because we have our victim having a indirect family connection to the same outlaw motorcycle gang that our perpetrator is involved in. Now, in this particular example, we also know that one of the things that caught the eye of our investigators is that Lewis Hughes' wife, Karen Elliott, also had her car stolen at a similar time. So we'll get that representation of that on the screen. And we can see here that Karen Elliott had a car that was involved in a crime with Jessica Kelly. We can see Jessica Kelly has actually been involved in several car-related crimes. I can go through and analyze to see if they're all car-related crimes, but I know in this particular example. And we can see here again, there's something suspicious here when we right-click on Jessica and we say proximity to organized crime. What connection does she have? And again, we see an obvious connection between her and the Hells Bells outlaw motorcycle gang. So something's going on here in this particular example. We have, too much proximity between perpetrators and victims to this Hells Bells outlaw motorcycle gang. So the next thing that might be interesting for me to do is to do a multi-selection action. So I'm going to select Billy and I'm going to select Lewis Hughes, and I'm going to run an action saying, have they called each other? And essentially what this is going to do is traverse the graph to find if there's any phone calls that have happened between these two individuals. If I run that action, I can see there has been phone calls between Lewis and Billy. So the phone that's registered to Lewis and the phone that's registered to Billy have had a phone call with each other at about 1 o'clock in the afternoon. We can see there the call time on the right hand side. So again, our victim and our perpetrator are maybe a little bit too closely related to one another for this to be a believable story. If I did the same thing for Lewis Hughes and Jessica Kelly, have they called each other? Again, I can see a call connection here. And in this case, the phone that's registered to Lewis Hughes has actually been involved in 2 phone calls with Jessica Kelly. So we're starting to see some connections here between our victims and our perpetrators. What we want to do now is to analyze, use the temporal and the geospatial tools to see if there's any more clues or any more interesting pieces of information with this network that we have on our screen now. So I'm going to open up the analysis tab on the right-hand side. The first thing I'm going to do is geospatial, enable the geospatial view. Just zoom in, see this is all happening in the Manchester area. And I'm just going to remove some of the things that I'm not interested in seeing geospatially. All I want to see is the crimes that were on my canvas and the persons that were on my canvas represented in a geospatial way. And we've predefined how we want these people and crimes to be represented on a map. If I zoom in, I can see locations for Jessica Kelly, Ernest Thompson, Billy Moore, and Karen Elliott are all quite far away from where these car crimes are happening. But if I zoom in a little bit closer, I can see Lewis Hughes has actually got quite close proximity to where these car crimes are happening. One in particular, he lives on one side of Queen's Park and the crime has occurred on the other side of Queen's Park. So maybe significant, maybe not significant, but a geospatial representation of those crimes and of those persons of interest that finds something interesting in this particular example. What is interesting though is if I open up the time bar view, we can see here, I'm going to turn them all off again. I want my crimes and I want my phone calls represented temporally. And what that has done there is created this time bar view at the bottom that represents the frequency of the crimes and the frequencies of the phone calls happening. And we can see there's some co-location between the phone calls and between the crimes. And what this is actually telling us is that on the day of the crimes, on the day of these car thefts, Lewis Hughes has made a phone call to Billy Moore. So victim has made a phone call to perpetrator. Again, on the day that Karen Elliott's car was stolen, we have a phone call between Lewis Hughes and Jessica Kelly. So again, adding some validity or adding some context to the fact that there's something suspicious going on in this particular example. Now, obviously, this is completely fabricated data. We've made things nice for this particular demo, but it's just to articulate some of the different tools and capabilities that you have available in the Hume platform. So you have your actions that allow you to do really advanced graph traversals and graph analyses with the click of a button. You have geospatial analysis that allows you to put those nodes on a map and analyze their position. You have temporal analysis that allows you to analyze when certain events and when certain things are happening across time. So quite powerful capabilities, all within a single canvas with multiple sources of information all represented on that same canvas. The last thing I'm going to show you, I'm just going to turn off my time bar view. The last thing I'm going to show you is styles, and styles allow us to basically calculate or calculate parameters on our canvas and change the visual representation of what's on our canvas based on those calculations. We've got one pre-prepared for us here, the pole viz, and essentially what this does is it does a few things. It calculates our crime score, so crime risk score of 100, and represents that score on our entities of interest. It also calculates another criminal risk score that's represented as a donut as well. And then we have the badge down the bottom, that red badge down the bottom, to represent the attributes that exist either on that particular entity or calculated on the information that surrounds that particular entity. So these are some pretty basic examples of styles that can be applied, but we can look at surrounding information, actually do graph traversals to calculate something and to change how the graph presents to users visually. Okay, that wraps up my presentation and my demo, Andre. I don't know if you've got some. I can see there's some questions in the chat. Did you want to ask them to me?
Yes. So first of all, thank you, Dan, for the presentation. It was amazing, and for the demo. So I have a few questions. I answered a few of them online, but for the rest of them, let's take them to public. So can I run network analysis like community detection, centralities, path findings, algorithms, and these things?
Yeah, absolutely. So Neo4j has something called Graph Data Science, or a package called Graph Data Science, that has dozens and dozens of graph algorithms like centrality, betweenness, Jacquard similarity, all these kind of graph algorithms that you'd be used to and expecting within it. So those from a Neo4j perspective are available out of the box with Graph Data Science or with the GDS package. If you have GDS in your Neo4j instance, you can reference all of those GDS capabilities in Hume as well. So you can actually reference them in actions, you can calculate things on the fly, and actually tap into that that power of graph data science and those algorithms with the click of a button. So really powerful to be able to make those complex graph algorithms and those complex graph data science available to intelligence analysts, at the click of a button through the actions.
Perfect. Another question, you mentioned orchestra in a bit, and there's a participant asking, can I stream data from sources like Kafka or ingest data from APIs?
Yeah, most definitely. It's one of the more common use cases for Orchestra is to be that streaming connection. So we can set up workflows to read from Kafka topics. We can read from a number of different connections, but Kafka is one that's quite common. But we can take those Kafka messages, we can process them in a certain way using flow files and using flow management, and then write them to the graph in a specific way. So we have connections that you can either do it in code, so you can have your Cypher code snippet that'll take that information from a Kafka topic or from whatever API connection you want and write it to the graph, or we have some visual connectors where you can actually map the file visually to the schema that you want it to write to. So yes, absolutely quite powerful tools and capabilities for streaming in Orchestra.
Another question, how does Hume or Neo4j logically separate data clusters per case or logical custom unit, and whether can databases be ingested and mapped to previously used logical segments? Like in an old world, there could be cross-database references.
Yeah, so generally what we try to do is, like in that poll example, we're trying to take the source systems and merge them into a single schema. But there's no reason that we can't have a domain specific graph set up for a specific source. So to have a one-to-one connection between a source data set and a domain specific graph, and to try and represent that information fully. I don't know if I've answered that question fully, but that's what I'm thinking is the answer that I have. Yeah.
Perfect. Another question concerns the data. So to get all the data analyzed, do we need to store the data on our end, or is the data staying with the customer? How does this work?
No, very much the data is staying with the customer. So Neo4j and Hume are installed either on-premise or on cloud environments that are managed by these organizations' infrastructure teams, and then the data is ingested in. So we're not, setting this up as a software as a service or a central service for law enforcement or intelligence agencies. These are instances of Neo4j and Hume that are installed either on-prem or on cloud instances managed by these organizations.
Perfect. Can specific connectors be built to custom made to ingest data into Hume? How flexible is it?
Yeah, so we already have a lot of flexibility with Orchestra for data connections. However, if there's something that we don't have, we have many examples of where we develop something, specific or custom for, maybe some older databases that aren't, regularly supported by JDBC or ODBC with that tool. But yes, we do have experience building custom connections with, odd databases or databases that aren't commonly seen.
Perfect. We got time for our last two questions, so I'll just pick some and then answer the rest of them offline. So first of all, does Hume need internet connection to work?
Not necessarily an internet connection. If it's stored on-prem, you need some kind of network connection, but not an internet connection. So it's not a cloud, doesn't have to be a cloud-based tool. It can be installed on-premise. Most of the instances in law enforcement agencies at the moment are on-premise installations. So you need some kind of network connection to the system to be able to connect to it, but not necessarily a connection to the public internet. No, if it's an on-prem installation. If it's a cloud-based installation, then there is some, obviously there's some connection to the internet required.
Perfect. And I think last question will be, if data is stored in a specific document, e.g. case report, can you reference this document and make it available in the graph as a note in relations to all the details in the doc?
Yeah, there's some really great GraphAware blog posts about us doing this. So what I will say is that GraphAware doesn't provide any algorithms for extracting entities from text. However, we provide the destination for that extracted information to be stored and visualized for intelligence analysis. So there's many entity and relationship extraction algorithms that are constantly being developed and improved in the industry. We can essentially use those algorithms to extract entities and relationships from text and then represent those entities and those relationships that have been extracted in a graph database, either in a specific domain graph that's just related to documents, or we can summarize that information and put them in the pole graph or put them into a tactical graph, depending on the use case. So graphs are a fantastic way of, let's say you have 1 million documents. Graphs are a fantastic way of extracting the unique entities between them and seeing the connections between all of those documents. And there's some great articles online from GraphAware about how to do that.
Perfect. Thank you. We are at the hour. So Dan, thank you very much for the presentation, for all the answers. Thank you all guys for participating, for joining us. As I said, you will receive recording your email in a few moments or hours, depends on how fast it's processed. So then you can go back to everything you've seen, and you can also always contact us to hear more, see a demo personally tailored to your use case, and we'll be looking forward to hearing back from you.
Yeah,
Thank
and if I haven't got to any of the questions that are out there on the line, then you can reach out on LinkedIn. You can find me at Dan Newland, or reach out at email. It's dan@graphaware.com if there's any other questions for the presentation specifically.
Thank you very much. Bye-bye.
Thanks all. Bye.